Lab 4, Circuits. Introduction. We will simulate virtual circuits and find the potential difference in conventional current. We will also be applying the circuit analysis principle using the loop rule, capacitors, resistors, and EMF, also known as our battery, to find our potential difference. We will also be comparing the idealistic versus the realistic experiment. For our first circuit, we have two batteries that hold 3 volts combined, 1.5 volts each, to form a circuit with two resistors, and we connect two ammeters to them. Because the circuit is in series, we are able to add our resistors being 47 ohms and 100 ohms to get approximately 147 ohms of resistance. We can use this to find our conventional current, which is defined as the voltage is equal to conventional current times the resistance. By isolating our variable, we're able to find our conventional current to be 0.0204 amps, and also by definition, because we are in series, our conventional current I2 is equal to I1 at the different locations of the ammeters. For our simulated model, we have that the conventional current is the amount of mobile charges passing through a finite distance of wire measured in coulombs per second. We also have that the potential difference from one end of the circuit to the other is 3 volts, which is the difference of the batteries. This is basically what we did in the last slide. So we have both our resistors and our ammeters reading approximately the predicted value, along with our potential difference from the batteries being 3 volts. To continue our model, we are able to break the circuit into smaller pieces. By using the loop rule, we are able to add each different segment of the circuit, and by definition, it will always equal to 0 volts. By doing this, we can find the potential difference between each individual segment and piece. Notice that our voltage in the section AB is 3, from CD is equal to -1 volts, and from E to F is equal to -2 volts. And the rest of it has no influence, so it will equal 0 volts. And in total, our sum is equal to 0, which satisfies our definition. We are able to find our resistance, VCD, by applying to a similar rule from a few slides ago to find our R47, or resistance, and also across the voltage CD. They'll also find the resistance across EF. For the next part, we designed an RC circuit to charge our capacitors while using one battery and a light bulb. Our initial conditions had two trials. The first one with a 9-volt battery, 200 farads capacitor, and 10 ohm bulb. The second one differs as we have a 20 ohm bulb instead, and we are trying to find our charge time results. The first one being 10.53 seconds, and the second one being 13.53 seconds as we increase the ohms of our light bulb. The key idea here is that our discharge times must be proportional to the resistance and potential difference. Next, we will be discussing the potential difference of our previous circuit. By definition, we have that our delta V is equal to delta V naught e to the negative t over RC. We can easily rewrite this and break down the terms to find our RC, which, if we have our voltage ln of V over V naught versus time, we can use the slope of this to plug back into our formula, where it's -1 over RC is equal to our slope to isolate our RC variable. The real experiment questions versus ideal. So what would be different if we used a real ammeter versus our simulated? In the simulated, we assume that there is no interference of electrons from the ammeter and wires. However, this is not the case for real life. We would have a lesser recorded value because these components have resistance on them. And what about our real battery to charge our capacitor without resistors? There still exists resistance from the batteries and capacitors, same with the same principle as our last question. So, the greater the resistance leads to the slower conventional current with a constant potential difference. The time to charge would decrease significantly as the chargers move very fast in real life.